So you've learned some neat little tools to look at resistor networks and to solve some DC circuits. This is indeed the most important chapter of this semester, because if you're ever going to see something again, you're going to see some circuits. In engineering, whether you're mechanical, electrical, civil, you will see circuit analysis. If you go into medical fields, the human body is a circuit. The nervous system is a DC circuit. So these techniques that you'll see in this chapter will apply to the human body as well. So this is indeed the most important chapter, and what you're going to learn in this lecture might be the most important idea of the whole semester as well. Specifically speaking, we're going to look at the branch current analysis of circuits, sometimes called the mesh analysis or nodal analysis. There are different forms of it. If you change it slightly, you get these other forms, but ultimately it's the same idea. And so we're going to look at this analysis and give you a straightforward way of approaching circuits, hopefully without having to think too hard. That's the purpose. So we have Kirchhoff's voltage rule, and if we describe this, the voltages across all the elements around any closed circuit loop must add up to 0. This is a key point. What it's saying is if I were to start at some point in the circuit and walk my way around the circuit going anywhere I wish, walk around, if I ever come back to where I started, all of the voltages I encountered along the way, positive or negative, added up together will add up to 0. Because I'm going to end up at the same potential where I started if I come back to where I start. A mechanical analogy to this would be if I were to go out hiking, and let's say I start at some point, and I go hiking over a mountain or a hill or something, and I walk all day along different levels of that hill, and I'm walking all over the place. But if I ever come back to where I started, then the total height that I encountered over the course of that day will be 0, because I'm back at the same level at where I started. And so in a circuit, if you start at a certain potential, which is the height within your electric field, and come back to that potential, your total change in potential will be 0. So we're going to use this as the central key to this idea of branch circuit analysis, branch current analysis. So let's look at this simple circuit here. We have a battery of voltage V. We have a resistor R1 and resistor R2, and we have a starting point. And if I were to approach this from a physics perspective, I would say that the battery is supplying a potential difference. So that's my potential hill, if you will, for this circuit, as my positive charges are falling from the top of the hill down to the bottom of the hill. And as they fall, they go through a potential drop across resistor 1 and a potential drop across resistor 2. So if I were to describe going around this circuit, I could say that I have a positive voltage for the battery, a potential drop across resistor 1, which is by Ohm's law, current times resistance 1, and another drop across resistor 2 by Ohm's law, which is V equals IR, current times resistor 2. And I get back to my starting point, that should equal 0. Sounds good. So the fact that we return to our starting point means all the voltages add up to 0. We're going to try a little trick here, though. We're going to start with this equation that we just constructed, which caused us to think a little bit. We had to think about, going up a battery and then going down potential drops and all that stuff. We don't want to think that hard. So we want to find a way to approach this equation and come up with these equations without having to think. So here's a trick. We're going to multiply this equation by a negative 1. Both sides of the equation by a negative 1. 0 times a negative 1 is 0. And so we have a new equation which is equivalent to the old, and it looks like this. Negative v plus IR1 plus IR2 equals 0. Totally equivalent equation. I can get this equation if I do this. If I look at the battery and I assign the positive terminal of the battery a plus sign and the negative terminal of the battery a negative sign, so the positive terminal is the long line and the negative terminal is the short line. So I'm going to mark the battery positive for the long line, negative for the short line. Like that. Then, wherever the current enters a resistor, I'm going to call that the positive end. And wherever the current exits a resistor, that is the negative end. So with this current going left to right through resistor 1, I will have positive, negative on that. As it's going down top to bottom through resistor 2, I will have plus and negative there. Wherever the current enters, positive, exits, negative. So now I have all my components marked positive or negative. Now I select any starting point I wish in this circuit and I start walking. I'll select this starting point. I can walk any direction I wish, walk anywhere I wish in the circuit, but as long as I come back to where I started, everything I add and subtract along the way is going to add up to 0. And in fact, the way I would decide what I'm going to add or subtract is that as I'm walking, if I walk into the negative end of something, I will subtract that, or that'll be a negative voltage. If I walk into the positive end of something, that will be a positive voltage. So for instance, if I walk around this circuit clockwise, then I'll go into the battery, that'll be a negative V, and then I'll have plus IR1, and then I'll have plus IR2, and then I come back to where I started, equals 0. So without thinking too hard, with all these components marked, I just walk around and I come up and add or subtract my voltages to equal 0. I come up with the same equation. Let's try this out on another circuit. This circuit right here with 3 resistors and a battery. First thing I'm going to do is I'm going to mark my battery positive or negative. Assign a positive to the long bar, a negative to the short bar of the battery. Next thing we're going to do is I'm going to assume current directions. Now here's the only arbitrary part of this whole analysis, is that you can actually choose any direction you wish for these currents. The only stipulation is that you must be consistent throughout the rest of the problem. Once you decide your current directions, you've got to stick to them and analyze the problem totally with your assumptions. So you want to make good assumptions, but you can make any assumptions. You know, it's possible you might come up with a negative current at the end, and maybe your current's going in the wrong direction. So 2 negatives make a right. In other words, 2 wrongs make a right. That's okay. It's okay to have a wrong direction with a negative current. That's okay. But we'll just go with whatever you do. We have some intuition as to go with this, though. I'm going to go with the battery. Whatever, if my battery's in a branch, whatever direction the battery's oriented, that's probably a good direction to select for the current in that branch. So as I'm going negative, positive here, I'm going to assume that my current is going, in essence, out of the positive terminal of the battery. So for my branch number 1, I'll assume a current going clockwise through that branch. Now as that current encounters this junction up top, it's going to split. Some of it's going to go through branch 2, some of it's going to go through branch 3. And hence I'll have I1 as the current flowing into that branch, or into that junction, and I2 and I3 are flowing out of that junction. So immediately I could say that I1 current is equal to I2 plus I3, because what flows into a junction must equal what's flowing out of a junction. So we made these current direction assumptions. Once we made these assumptions, we can mark all of our resistors. Positive for where our currents flow into the resistor, negative for where they flow out. So for each resistor, we're going to do that. For this 4 ohms up top, I1 is flowing into the left-hand side and out the right-hand side. So we're going to have positive, negative there. For the current I2, top and bottom. For I3, top and bottom as to flowing in and then out. So now everything's marked. We got the batteries marked, we got the resistors marked, and now we're ready to start walking. We'll select any starting point we wish, and we'll walk around any loop we wish, any direction we wish, anywhere we wish. As long as we come back to the starting point, everything we add and subtract along the way will add up to 0. So, for instance, if I were to go around this left loop, and let's go clockwise. So if I were going clockwise around this left loop, I would have a negative 12 volts plus 4I1 plus 3I2 equals 0. And that would be my left loop result. So I have an equation with 2 unknowns. If I were to go around the outer loop and bypass this middle branch, I'm just going to go around this outer circumference loop, then I would have a negative 12 plus 4I1, and then going over here, plus 6I3 equals 0. If I were to go around the right loop, I would have a negative 3I2 plus 6I3 equals 0. And so I have 3 equations with 3 unknowns. This is solvable. I actually have a 4th equation by current division. Up top here at this node here, I would have I1 flowing into that node and I2 and I3 flowing out. So it's clear that I1 is equal to I2 plus I3. Equivalently, I could have selected the starting point as my node, and I have I2 and I3 flowing into that node and I1 flowing out. So I2 plus I3 equals I1. Doesn't matter, it's the same equation. So I have 4 equations with 3 unknowns. Definitely solvable. You always need as many equations as you have unknowns to be able to solve it. Here we have 4. Let's say we wish to find current I1, which is the current in the first branch. I really only want to look at the loops excuse me, that have I1 in them. That's going to be the left loop and the outer loop. I really don't need the right loop because that's concerning current I2 and I3. I want to solve for the other currents in terms of I1. So I'm going to focus on the left loop, which has I1 in it, and the outer loop that has I1 in it as well, and then use the current division equation as well. So that'll give me 3 equations that I need. So solving the left loop equation for I2 in terms of I1, I would have 3I2 equals 12 minus 4I1 divided by 3. Current I2 is equal to 4 minus 1.33 I1. Good. I have I2 in terms of I1. If I solve the outer loop equation for I3 in terms of I1, I would have 6I3 equals 12 minus 4I1 divided by 6. I3 is equal to 2 minus 0.67 I1. Great. I have I3 in terms of current I1. Now with my current division equation, I know that I1 equals I2 plus I3. Substitute in I2 and I3 from these previous equations into this one equation. Now I have I1 is equal to 4 minus 1.33 I1 plus 2 minus 0.67 I1. I have one equation with one unknown. Solve for I1. So I have 1.33 plus 0.67 plus 1, which is 3 times I1 is equal to 6. Or I1 is equal to 6 divided by 3, 2 amps. Sounds good. I've got the current. I've got I1, the current in the first branch. And since I've got that current, the other currents follow quickly because I have them defined in terms of I1. So I2 is going to be 4 minus 1.33 times I1, 2 amps, which is going to be 1.33 amps. And I3 is 2 minus 0.67 times I1, 2 amps. And that's going to be 0.67 amps. And note that I2 plus I3 does indeed equal I1. Also note that all my currents came out positive. So my original assumption of the directions of the currents were correct. It wouldn't matter a whole lot. It's okay to come up with a negative value for currents and have a wrong direction. That's okay as long as you stick to it. But in this case, we can stick to these results as well. So it's kind of good maybe to use your intuition to come up with the correct positive currents at the end. All right, let's try another circuit. This time, though, we're going to have 2 batteries. So we're going to complicate it a little bit, add another battery in there, see how this technique will work on this kind of circuit. First thing I'm going to do is mark my batteries, positive or negative. So I'm going to look at this 14-volt battery. The long bar is positive, short bar is negative. This 10-volt battery, long bar is positive, short bar is negative. So I'll mark them, positive, negative, positive, negative. Sounds good. Next thing we're going to do is assume current directions for my 3 branches, I1, I2, and I3. The question is, I do have some intuition that I wish to use for this, especially for the branches that I have batteries in. I'm going to go with the orientation of my batteries as far as choosing my current directions. So because the 14 volts is oriented from right to left, and I want my current coming out of the positive end, then I'm going to have my current going counterclockwise in that first branch, the top branch. Because my 10-volt battery is oriented from left to right, I'm going to have my current going from left to right in that branch as well. So I have my I1 going at least through the top part, going counterclockwise. My I2 going left to right. What about I3? It has no battery in that branch. What do I do about that? Well, if I look at this junction here, where the 3 currents are coming together, I have I2 flowing into that junction, and I have I1 flowing out of that junction. I1 has a 14-volt battery in the branch. I2 has a 10-volt battery in that branch. I might have an intuition that I1 is going to have a greater magnitude than I2 because it's got a greater battery voltage in its branch. So if I1 is bigger than I2, I'm going to need something to supplement I2 in order to make I1. In other words, I1 is coming out of that junction, I2 is going in. I'm going to need I3 going in as well, so that I2 plus I3 equals I1. That's what I want, and those are the directions I'm going to assume. So we have I1 flowing out of that junction with the battery direction. We have I2 flowing into that junction with the battery direction on that branch. And I'm also going to have I3 flowing into that junction such that I2 plus I3 equals I1. In fact, that'll be my first equation. Current I2 plus current I3 equals current I1 by current division. Okay, what do I do next? Well, now I know my current directions. So based on these directions, I'm going to mark all my resistors. Wherever an assumed current flows into the resistor, that's the positive end. Wherever it flows out of the resistor, that's the negative end. So I1 is coming around like this. It's flowing in the top end of this 4 ohms and out the bottom end. So I'm going to have positive, negative for that current. It looks like it started at the bottom. I3 is going in the left end of the 2 ohms and out the right end. So I have positive, negative there. I2 is going in the left end of the 6 ohms, out the right end. So I have positive, negative there. And then I1 is going top to bottom through the 4 ohms. Positive, negative there. So I have everything marked. The batteries are marked. The resistors are marked. I'm ready to start walking. I need to choose a starting point. And let's say we want to find I1. We're only going to choose the loops that have I1 in them. So in this case, I'm going to choose the top loop and the outer loop. I'm not going to worry about the bottom loop because that would relate I2 to I3. I don't really want that information right now. So I want to do the top loop and the outer loop so that I can have the loops that have I1 in them. If I start here, and I'm not sure which way I went either, it doesn't really matter whether you go counterclockwise or clockwise through your loop. It doesn't matter. Everything you add up will equal 0, and you could always multiply -1 on either side. You would get the same equation. So it doesn't matter how you walk through the loop. It doesn't matter where you walk through the loop. It doesn't matter which direction you walk through the loop. As long as you come back to your starting point, everything adds up to 0. How great is that? So it looks like I went this way. -4I1 plus 14 minus 6I2 plus 10 equals 0. And that is my top loop equation. I want to get I2 in terms of I1. So I'll have 6I2 equals 24 minus 4I1 divided by 6. I2 is equal to 4 minus 0.67 I1. Good. Let's do the outer loop now. If I look at the outer loop, I'm going to start from the same starting point. If I go clockwise, I'll have a -10 plus 6I2 minus 2I3 equals 0. So, I want to do the outer loop. Okay, I just did the bottom loop and I didn't want to do that. All right, good. -4I1 plus 14 minus 2I3 equals 0. That's the outer loop. I didn't want to do the bottom loop. Solve for I3. I have 2I3 is equal to 14 minus 4I1 divided by 2. And I have I3 equals 7 minus 2I1. So now at this junction, I have Kirchhoff's current rule. Whatever's flowing into the junction should equal whatever's flowing out. I2 plus I3 equals I1. And now I'm going to substitute in for I2 and I3 from what we just previously got. So we have 4 minus 0.67 I1 plus 7 minus 2 I1 equals I1. Add up all the I1 terms, add up all the constants. So I have 11 is equal to 3.67 I1, or I1 is equal to 11 divided by 3.67, 3 amps. My other currents follow. I2 is equal to 4 minus 0.67 times 3 amps, 2 amps. And I3 is equal to 7 minus 2 times 3 amps, 1 amp. And the fact that these all came out positive means I did assume the correct current directions. And note that I2 plus I3 does indeed equal I1. So I got all my currents. And it's a two source circuit, no problem. This method, 2 sources, 3 batteries, 4 batteries, bring it on. Doesn't matter. this method will work for all of them. I could get these results that we just got using linear algebra and Cramer's rule and determinants in linear algebra to do it. This is how I might do it. Set up my three equations involving I1, my three variables, and the constants involved in this form. And I can do my denominator determinant, which is just the coefficients of my variables in a determinant form. So I want to solve this determinant with my coefficients, negative 1, 1, 4, 6, 0, 2, 0, 1. One way I like to do these 3 by 3 determinants is to repeat my first two columns, and then I'm going to do all my diagonals, add these three diagonals going down this way, and then subtract the three diagonals going up the other way. So for my first diagonal, I have a negative 1 times 6 times 1, which will be a negative 6. Then I have 1 times 0 times 2, which is 0. Then I add 1 times 4 times 0, which is 0. And then I'm going to subtract 2 times 6 times 1, so that would be a negative 12. Subtract 0. Subtract 4. And I have a negative 6 minus 12 minus 4, negative 22. That is my denominator determinant from Cramer's rule. So to find my I1 determinant, I substitute my constant column for my coefficients in the I1 column. So it looks like this. And again, I want to solve this determinant. So I'm going to repeat the first two columns and do my diagonals as before. First one will be 0 times 6 times 1, which is 0. Then I have 1 times 0 times 7, which is 0. 1 times 24 times 0, which is 0. Minus my other three diagonals, which will be minus 42, minus 0, minus 24, which will give me a negative 66. Hence, my I1 is equal to this determinant divided by my denominator determinant. I1 is equal to negative 66 divided by negative 22. That's 3. I could do the same with my other variables using the same denominator determinant in each case. For instance, if I were to try to find I2, take my constant column, substitute that in for the coefficient column for I2, I get this determinant here with the 0, 24, 7 being in the middle column. To solve this determinant, I'm going to repeat my first two columns and again do my diagonals. So I'm going to have negative 1 times 24, 0 for the second column, and 4 times 7, 28 for the third column, or third diagonal. So negative 24 plus 28 going down. I'm going to subtract the other three diagonals. So I'm going to have a minus 48 minus 0 minus 0. So it's going to be negative 24 plus 28 minus 48 gives me negative 44. And my I2 then will be negative 44 divided by negative 22, 2 amps. You can see where this is going. If you wish to find I3, just substitute in your constant column for the I3 column and do the determinant of that divided by the denominator determinant negative 22, and you would get negative 22 over negative 22, which will be 1. So that's he would use Cramer's rule to solve this. I think it's a little bit easier just by doing the substitution ideas that we did earlier for these branch current analysis. But this is one way you can use linear algebra to solve for it as well. Okay. Now here's I3. Let's say you want to find the voltage difference between 2 points. If you want to do something like that, all you have to do, let's say A and B, which is not marked on here, Well, let's say you wanted to find the voltage difference between 2 points in the circuit. Here are my currents. I didn't want to do that. How do I go back? Okay. For instance, let's say I want to find what is VA minus VB if A is up in this corner and B is down in this corner. To find the voltage difference between 2 points using this method, all you have to do is walk your way from point A to point B and add your voltages as you go from A to B. So if I were in this corner and I wanted to find the potential difference between this and this, I would simply walk any path I wish to get to there. In this case, it'd simply be plus 14. That would be it, 14 volts. I could walk this way, which would have been a plus 4I1 minus 10 plus 6I2. If I did 4I1, which is 12, minus 10, which will leave me with 2, plus 6 times I2, which is 12, that gives me 14 volts as well. Or I could go plus 4I1 plus 2I3 gets me there as well. That would be 4 times 3, which is 12 volts, plus 2 times I3, which is 2 volts, 14 volts. It doesn't matter how you go from A to B. If you add the voltages between those points, you get the potential difference between those 2 points using this method. This is explained in more detail as you look at the Edu-Creation videos on specific problems in the problem set. So take a look at those and they'll explain this in those videos. But that's the way you would do it. And this is the branch current method, mesh analysis, nodal analysis, whatever way you wish to call it. This is the method to look at DC circuits. Enjoy.